calculation will work too today on Friday. So I just want to remind you guys, we did a lot of load calculation for motors. If you forgot, you can visit my YouTube channel under motors. You're going to find tons of calculations, so more than you can even imagine. I want to highlight, Chris, the DC motor this time. And the reason I want to highlight the DC motor is because last chapter actually that we talked about DC drives and AC drives. And we said if you have a DC motors are superior in terms of speed control. If you have a DC motor, then you need to be able to feed this DC motor, right? And the way we feed a DC motor right now is we take an AC three-phase system with a DC drive, convert it into the appropriate DC voltage, and dump it across that particular motor. We don't have a DC generator, so to speak. So we take an AC, convert it to DC. So anyway, you guys are familiar with this. We didn't talk a lot about, this is a full load current for motors that run at DC. The reason why I just want to highlight a few things. First, just get you familiar with the voltages that they run them at, the DC. Some of them are familiar to you, others are not. For example, 180 is not a typical distribution system that we use, guys. But actually, I want to remind you, these will be the outcome of the DC drive. So it's not like you're going to have a panel that's 180 volt and you're going to wire DC motors from them. You're going to have a DC drive that can spit 180 volt and from a 480 system and dump it across a motor. That's really what these are. So basically, the way we do them is you grab your overcomputation device, bring it into my DC drive, and then you put them here across the motor at the right, and make the drive at the right voltage, and you dump it across these motors. So that's what I want to highlight. So up to this point, Chris, from this side, you are looking at most likely 480 system. From this side here, you're looking at voltage DC that could be any of these voltage. Make sense? See how we can tie a DC motor, this is my DC motor into an AC system. You're not going to find a DC panel, so to speak. You're going to find a DC drive tied a DC motor into an AC system. Can I get you guys to understand that one? If you have a DC motor, conveyor, whatever that runs with DC. Anyway, so that's it. If you understand, then you start with specifying the drive. Then you're going to size the conductors right in here that go into the DC, and the overcomputation device that protects the DC and so forth. So what you can do is I want to grab just one 7.5 horsepower motor. This comes full load amp from the NEC at these values, exactly typical. And the way we size them, Chris, if you're sizing a conductor, 1.25. If you're sizing current protection device, we size them based on the overcomputation device rule. Overload, the same rules. The only thing is you just pick the right conductor. And how many conductors we use if it's a DC motor? 2 conductors, right? Your positive, your negative, coming into your DC. You're pulling a DC, 2 conductors, and of course, don't forget the ground. This is my positive, my negative conductor, and we are pulling a ground, of course, a grounding system. Any comments, guys, about the DC system? Any comments about the DC? Hey, good morning. So that's on the AC side, guys. On the AC side, you take the AC part of the drive and you size it based on a 480, basically, or AC, and you size for a motor based on if it was an AC motor. So the 1.25 times the full load current of the drive, and then if it's an overcomputation device, 2.5 or whatever the multiplier, the overcomputation part they use. I want to remind you, they make them typically, you can go higher than that, up to these 200 horsepower motor, superior in terms of speed control. That's the only reason why we use them. High maintenance, very high maintenance. Any comments, guys, about using this? How to tie a DC system? Let's just say we're going to power this one at 240. So I brought a drive that takes me from 480 to 240. At 240, and I'm burning my DC motor at 240.
So, what kind of DC system did you have, or DC, what would you be driving?
You're driving the motor. The motor is DC.
Right. But conveyor. Okay.
Load.
The load.
Load. Oh, you can drive a fan. You can drive a pump. You can drive, I see what mechanical load. A conveyor. You can drive a lift.
So anything
can-
that you can start slowly and stop.
Yeah, or anything, as a matter of fact. Fan. The speed control. If you want something speed control, good speed control, they're superior. I don't like to even talk about this because of the VFD guys. The VFD replaced all this with one big fat VFD with a motor, and you get to speed control. The reason why they became popular, these guys, for speed control. So if you get the speed control out of a DC motor, it's inferior to the AC induction motor, for the most part.
When did the term drive replace the term rectifier? Did someone do something?
I don't know. A lot of them say AC and DC drives. It is a rectifier
Yeah.
for all practical reasons. Yeah,
Rectifier or converter.
Yeah. 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 Rectifying AC, inverting back to DC. Rectifying AC to DC, inverting back to AC. Okay.
Coding scheme for when you're running plus minus stuff that's common in convention to that.
Any what?
Is there a convention to the conductor color that you use?
Color conductor, good point. Color conductor, you have most likely the grounded. The only conductor that the code cares about is the neutral. Typically the negative conductor. So when you come over here, here's my positive. Where's my positive, Chad? Oh, okay. The positive will be brown, blue, whatever color you want it to be, ungrounded conductor. And the negative will be grounded conductor, and it will be white. Now, if you don't ground the negative, then it becomes ungrounded conductor, and you can use any color you want, other than white or gray. So,
Like an electronic red and black on a typical color
red and black for DC, that's ungrounded system. Absolutely, that's an ungrounded system. Red, black, typical. If you ground the negative, then you're dealing with a grounded conductor, you have to apply the white or the gray on it.
Is it pretty typical to ground the negative?
I don't think so, not on the drives. There's no value for grounding the negative on a drive, but my understanding. Good point. But if you go to other application though, in the UPS system, they ground the neutral, the negative. They take the negative to the ground. Because you're dealing with a distribution system, not just with a drive. You have a whole distribution system. So the second thing, guys, that's not commonly used, I'll show you a picture of it, is the two-phase system. Oh no, I'm sorry, this is my single-phase system, full load current single-phase system. We talked about this when we were in the residential. The only thing I want to highlight here, Chris, is the range of the voltages. The range of the voltages. This is very interesting. So if you have a voltage from 110 to 120, it goes to 115. If you have a voltage from 220 to 240, it goes with 230. These two voltages are stuck by themselves. Can you guys see that? So if I have any voltage between 220 and 240, it goes to 230. Any voltage between 110 to 120, it goes to 115. The other two voltages are stuck. This is very confusing, guys, for a lot of people when you have a 200-volt motors. I always ask, are there 200 horsepower motors? Yeah, there are 200-volt motors. But the most common ones on a DC, the most common ones, as we all know, is going to be your 120 or 240. Your 120 or 240. That's the thing. I'm going to go back into the two-phase system. Without getting into the two-phase system, is not worth getting into it, but if you want any wiring, how do they wire the two-phase system? Check in here, guys. There's a two-phase system that wired with 4 wires. Really weird. Not commonly used now. It's the exception. So that's why they say the two-phase system and 4 wire. Look at the word that they use with it. Two-phase system, 4 wire. So here's two wires from the phase 1 and 2 wires from phase 2. And so that's how they do the two-phase system. The angle between them is 90-degree angle. So you have phase A and phase B, and 90-degree angle between them. Unlike the single phase system actually is hot 1 and hot 2. Because remember, this is a 240, this is a system 240/120, and the angle between them is 180. This is your single phase system. Your single phase system. This is your two phase system with an angle, with phase A, phase B, with an angle of 90 degrees. Who cares? It's all about how you put the coil inside the motor and wire it. That 90-degree angle, the way you wire the coil, gotta flip it this way, tie it from this end to that end. How many of these coils tied together? That creates an angle, electrical angle, and it decided if it's 180 degrees versus 90 degrees. So you can really create a lot of phases, multiple phases, more than 3 phases if you want to, by adding more coils. Anyway, 2-phase, not commonly used, very small applications for it, guys. I want to remind you of the voltage range that they use for it here, and the voltages that they use at the top here. And typical, you're going to go, I'm going to use the last one here, is a 200 all the way 4300, 43 at 43 amps at 2300 volt. I believe there's one building in St. Paul that's wired 2-phase. Other than that, and the way 2-phase guys create, I told you this story I guess before. First we came up with a DC. DC is great, give you an electrical system. Then we moved into the signal. We discovered the AC system, so that was more superior. You can send it longer distances. Then they start playing with the coils, create another coil and make it 2 phases. Okay, superior to the single phase. Then they add a third coil, and now here's a 3-phase, more superior. They kept adding, guys, and then they discovered after 3 coils or 3-phase system, really the advantage of adding more phases versus, so the optimum design, it's not worth it going higher than 3-phase system. Okay, so that's what I want to show. This is, you guys are very familiar with this one. I want to emphasize the synchronous machines, and the power factor here at the end. I want you guys to see with synchronous machine, they give you the full load current at a power factor, full load current of a power factor. Take this. Let's say we decided to go for a 460 motor, synchronous machine, and it's 41 amp, and the voltage, the horsepower is 40 for 41 amps. If the power factor for 90 and 80% power factor shall be multiplied by 1.1 and 1.2. Suppose that the power factor was 80. So the power factor here was 80%. Then you know what you need to do, Chris? You need to take this number and up it, before you even use it. Up it 1.25 to compensate for the lower power factor. If it was 90, then you up it 10% to compensate for the power factor. With synchronous machines, power factor are more effective with a full load current. With the induction motor, we care less. Induction and wound rotor motor, we care less. You guys are very familiar with this table, I know, because we used it a lot. I'm going to go pick up my favorite 200, and we'll get you, say, let's burn that baby at 240 3-phase, and here's my 480 amps. I don't know if you guys noticed, Chris, have you guys, if you look at this is 460, this is 240, so double that, right, for the most part, kind of, almost double it. Can you guys see that the current is almost double as you go through? As you double the voltage on the motor, the current almost, not 100%, almost double. So there's kind of almost 1-to-1 between, you go high in the voltage, the current will be cut by half. Every time you double the voltage, you cut the current by half.
Yeah,
Just observation.
pretty
Pretty almost there.
straightforward.
Yeah, almost they double it. Same thing if you get into, I don't know if you take this and this, press, and you see 4.4, cut it by 2.2, 6.4. But can you guys see this? Compare these two voltages together. Aren't they cutting it by half almost? Right? Take 4.2, cut it by half, give you this, 6.4, right? Almost. So just keep in mind, every time you double the voltage, you cut the current for the most part by half. So these are a couple of rules of thumbs to use. The other thing I want to highlight in this, guys, and I know we did a lot of calculation in them, is the high voltage, medium voltage. Like Chad was teaching yesterday, we were doing medium voltage. I want you to understand these are the only voltage, the medium voltage motors that you have in an AC control. If you have a motor that's higher than 2300 volt, you are on your own. You have to do engineering. So these are the voltages that we can get induction and synchronous motors at the higher voltage. And Chris, these voltages, they come with a system, they call it 4160 volt. You can feed them from 4160 or 24, most likely this particular one would be from a 2400 volt. So most likely these will be fed actually from a 2400, not 23, 24. You don't want to go for it. That's too high of a voltage for it. So this is the distribution system that Excel will give you to power these equipment. Any comments, guys, about the high voltages? Because we haven't talked a lot about the high voltage synchronous machines. Where would you use a high voltage? If you have in this case, I don't know where you justify at these horsepower using a high voltage, unless you have a high voltage existing there. Usually high voltage, guys, goes with high horsepower. For example, 6,000 horsepower motor. What would you do if you have a 6,000 horsepower motor? How do you power that one? If you power it, first of all, do you have a 6,000 horsepower motor here? Do you even, can you, the largest that you can get on a voltage 480, look at the largest that you can get is 500 horsepower. So higher than 500 horsepower, you are on your own. Most of the major manufacturing guys, they use higher than 500 horsepower. So what are you going to do? You're going to use the engineering documents that comes with the products and the nameplate for these motors. So can you guys see how I can't emphasize, we talk about these as if it's everything in the code. This is only limitation, very limited to 500. We you know, if you go to a shredder, the shredder that they use in St. Paul to shred your car, they pancake it first and they cut it into little pieces, then they melt it and make steel, and then they build bridges. That's their business, North Star Steel or Gerdau. If you go there, they have a shredder that running at 6,000 horsepower. 6,000 horsepower. And they are burning at 4160. So anyway, so these are beyond the limit of the code. Can I get you to understand the limitation? This is just, we know we use the code, we use these tables, but I'm going to highlight the things that I usually ignored in these tables. Does that make sense? So, because this is kind of sacred cow for all of us, where really this will cover you probably, I would say, Chris, in your career, these tables will cover you, and I like percentages, so I'm going to throw 70% of the time, this table will cover you. In most of commercial buildings, 70% of the time. There's 30% of the time you will exceed this table. Okay, and that's the largest cable that we have because it's 3-phase. The other thing, guys, is overload. When we do overload, and I highlighted this for you if you haven't done that before, this is your overload. Most likely you're going to have an overload, separate overload. And here's your multipliers. You guys remember the multipliers that we use? I know we use them. I want to emphasize one little thing, the service factor and the temperature rise. The service factor and the temperature rise. So please, again, this is just a quick overview. Most likely, if you have a well-respected motor, you will have a separate, they call them separate overload device. Separate overload device. Separate overload device, Chris, is you grab the overcomputation device here, and you put your overload at the bottom. And then you put your motor right in here. That's called a separate overload device. Here's one, and here is two. Separate overload, that's what we mean when we talk about these, separate overload. Now there's situation, Chris, like my student in Egypt is asking me about, is when you have only a motor and you have your overload is provided by this. So this is your overload and your overcurrent protection device. Both an overload and an overcurrent protection device. If you're in a situation like this, if you're in a situation like this is the same device, the circuit breaker providing an overload and an overcomputation device. Not good though, because it doesn't protect, it's not fully protected. Your motor will not be fully protected. You know what they do? Remember the overcomputation device, you cannot size the overcomputation device more than, when you can size it based on 2.5. So remember that 2.5 that we use, guys, multiplied by I full load current, right? So if you were to do it this way, this one is great with this overcomputation device. If you have one overcomputation device to protect the motor, then you're going to apply this rule, these rules on the overcomputation device. So let's just say my motor, I have a service factor 115, so I'm going to use this multiplier, and then this becomes 1.25 times I full load current. So you size the overcomputation device exactly like an overload because it have dual function. Does that make sense, guys? We typically don't do that. We do it a separate overload protection device. So we care less about sizing this 2.5. So we really don't care because we have a separate overload protection device. Any question? Can I guys get you to understand the difference between having one device give both and a separate device? Any question about that one? Just to give a simple example, if I like to use amps, suppose that this was 100 amp, and I know they're in horsepower, I'm going to use amps just to make it easier. If it's 100 amp, and so that will be 125 amp overload, and that will be based on this multiplier 250 amp circuit breaker, right? Go to this side, use the same 100 amp motor. This have to be 125 amp circuit breaker. Done. Can you guys see the difference? Now, if this doesn't allow your motor to start, too bad. But usually, guys, that's what typically they use in other countries. They match, but then you can go and match an overcomputation device with a certain manufacturer to your motor. So you're looking at more than just a general overcomputation device, a specific overcomputation device that goes with a specific load. So this could be done. And later on, who am I going to pick on here? Hey, William, Jackson. I want to pick on William, but Jackson can.
I mean, it appears that the circuit breaker would never go, because the other thing is always going to go first, unless there's a timing issue.
There's a timing issue, and there's a lot of stuff. The way they do it right here, guys, is then I'm looking for a space here to draw, and I don't want to make. So there's something called starting curve. Here's my starting curve on my motor. So the way they do a starting curve, this is my starting curve of the motor. Now, if you are to do it this way, then you have to design a tripping, a tripping curve of your circuit breaker that matches your overcomputation device. So you have to go to that specific manufacturer and get that curve, that setting, the long time pickup, long time delay, short time pickup, short time delay, and instantaneous. These are coming, guys. All this what I'm going to say is coming when we do the coordination. You're going to not only just size the circuit breaker, you have to have the settings, the internal settings specified for this circuit breaker so you can match it to provide an overload protection right at this point. So anyway, so you might have to run some analysis, or the manufacturer will tell you if you have this type of motor, you manufacture the motors machine, we recommend the following manufacturer circuit breaker with the following sizes. So you're basically using the manufacturer recommendation. Any questions about this? The other thing, I don't know if you guys can see here, larger. This is also, if you have larger than 1500 horsepower motor, they have embedded temperature detectors inside the motor. They don't, the overload protection device become worthless. What they do is they have embedded sensors inside the windings of the motor that they sense the temperature rise in the windings, and they give you real-time temperature detection, what's going on inside that motor. So before the motor starts smoking, you will have ample amount of time from your control system to look at, well, the temperature have reached this level. No, let's alarm. The temperature have reached this level. Let's trip. So there's a whole lot of calculation that you can do. So anyway, but for the most of you guys, probably 70% of the time, what we said will cover. There's another multiplier that you can multiply by 140. Motor's trip current of overcome devices does not exceed the following. If you're using an overcome protection device to protect it, they allow you to use this one. This particular one is actually if you're using an overcome protection device. Let's go to 430. We don't typically use it, but it's good. Good to go. If you guys go to 430, will you, to the overcome protection device? Go. Let's look at that one. Okay, separate overload, impedance. Okay, so that my thermal protectors, continuous duty, and larger than this. Okay. Okay, selection of overload devices where the sensing element or devices, okay, is not sufficient to start the motor. If it's not sufficient, this is where, if it's not sufficient to start the motor, that's what I thought. Okay, you can go higher than that. Selection of overload where the sensing elements or settings or sizing of the overload device selected in according to the steps before is not sufficient to start your motors, then you can do a different settings. 100. These are the exception. The rule, these are exception of the rule. Not the rule, exception of the rule to use them. Okay, so that's what I want to mention about the motors, guys. The second thing, you guys are familiar with this table. We used it before to find the inrush on a starting motor. So a lot of people, I'm going to use your table from that DC code book, and I want to give you guys just quick 50 horsepower motor and the voltage at 480. So I start for inrush. You take it's a design D. Remember that, how we did design D? You're going to take the upper limit, 4.49, multiply it by 50 horsepower, multiply it by 1,000, divide it by 1.73, and multiply it by 480. That will give you the inrush of your motor. So some of you will say, Chad, who cares? The question at this time, we have done it, who cares? Here's what the inrush is going to be giving you, guys. Take this. When I have my starting curve for my motor, this point right here is your inrush. You guys are going to be specifying this point. Well, who cares? Still, who cares? Because your overcome protection device is going to be sitting right in next to this one, Chris. And it's going to go somewhere here and come back to sit right into this area. So you're going to specify an overcome protection device that can go to the left of your starting current. Who cares? Still, who cares? You need an overcome protection device that allow you to start your motor. And if your motor does not start because stalled, after a predetermined amount of time, you want to trip right here. This is my time. This is my current I. So anyway, I'm not going to convince you later on, guys, when we do overcome protection coordination, please be aware that this number here is actually will decide that point for the motor. For example, if I have Chris my 100 amp motor that we just talked about, this will be most likely close to 600 amp. That's my usual, it's 6 times. So that point will be set at 600 amps. Who cares? Still, who cares? I need my circuit breaker to start tripping after 600 amps to avoid nuisance tripping. Now we're getting a little bit into the engineering side of it, guys. But if you're working as a designer, you need to know that. That's your next level. Unless you want to be drafting. So that point, this table is very important. We never talked about this table in terms of coordination. That point here is decided exactly what you did. That little table gets you the point here in the curve. Later on, Rob, when we use SKM software, that's you're going to see when you grab a 50 horsepower motor, it's going to draw a line like this for you, and that line, and you're going to see the point that says inrush point right here. You're going to know that this is the starting current of your motor. And the software will assign a typical code letter for your system. And if your system has a different code letter, it allows you to go change it from a B all the way into ugly S. Can you guys see the higher you go up, the more inrush on the motor, more torque you can get out of these motors, meaning more stress, mechanical and electrical stress on your electrical system and mechanical system. So please remember that line here, please, that line in this area, because we're going to be coming to it when we do the coordination.
Is that known as a short circuit rating then?
Short circuit rating is really slightly different than that. Let's go into that one.
What is the equation right there?
This is just the inrush, meaning if you have this type of motor, it's allowed to have this amount of current before smoke start coming out of it. Inrush, right? When you energize a coil, guys, the impedance, I'm sure you're explaining to when you energize a coil doesn't have a whole lot of impedance in it. Resistance, not a whole lot of resistance in the coil. When you energize it momentarily, most of the impedance is R. R is very small. So if you have a voltage divided by a very small resistor, you get a huge amount of current until the magnetic field build up in the coil. When the magnetic field build up in the coil, then the XL, the other component of the Z, start building up. So start being bigger and bigger after you energize the coil. So that's where the 10 seconds, that area here, that area right in here, the 10 seconds, that's the area that you're waiting only for 10 seconds, guys, not a whole eternity. Only for 10 seconds, you are waiting for your coil to energize so your XL gets bigger so the current goes lower. That's the nature of the coils. You energize the coil, there's an inrush of the coil. So it doesn't have to do the trip. The tripping curve, the tripping mechanism is right here for the overconduction device. Rob, my friend. So for example, if the motor if the motor did not stop right here, can you guys see that right at this point? If the current keep going, keep getting hot and hot, right at this area, you're gonna start tripping. Right, actually, right here, as you hit the overconduction device, the circuit, the overconduction device will realize that this is not a starting current. This is a ground fault or a short circuit inside the motor, and it will trip. I promise you guys, when we do the coordination, we'll throw we overlap them. So if you grab this green curve here and you overlap it over the red curve, every time you start your motor, it's going to trip. That's what the full load coordination between the starting curve and the tripping curve for the motor. Okay, the second thing I'm going to talk about, guys, is the overconduction device. And these are very quick review, as you all know. We're very familiar with this table. Rating we're setting for short circuit and ground fault. Okay, so you're going to have the first thing you need to do. I want to emphasize the things that I've never emphasized before. DC. Can you guys see the DC motors? DC motors way at the bottom. We haven't emphasized that one. DC current, constant voltage. That's your multiplier for your DC motor. We haven't touched on that, how to size that one. But really the multiplier. The other one is the synchronous motor. You have a synchronous motor. Chris, can you guys see the bottoms? We haven't touched on that one. Same thing, different multiplier. And if you have a wound rotor motor, also, these are your multipliers. These are the stuff that we did not touch before. We almost always, Chris, end up right here. We did these two, right? Single and three-phase. The second thing I'm going to highlight too is a squirrel cage other than design. Okay, squirrel cage other than design. these also the same multipliers. But if you have an energy efficient, if you have a design B energy efficient motor, guys, the impedance inside them is small to reduce the losses. So if you have a smaller impedance, you have higher rush on them. So look at this, how they, so we have, where are we here? They put you a 300, here stays the same, 175. Look at this, this goes very high here. The only difference really between these is this value. If it's a design B and you're using an instantaneous, just trying to find the, all of them are the same, right? Look at them, all of them are the same. The only difference up to this point is that value. Can you guys see that all these values are the same? The multiplier are the same. The only difference, if it's a design B and you're using an instantaneous trip, then you go up to 1100 kcm. Typically, Chris, you are using dual element time delay fuse. That's typically or inverse type circuit breakers. So you are right in here. Dual element time delay fuse or instantaneous trip. Typically, these are your common ones. The others can be used too. Any comments, guys, about this? So these are the most important thing. I just want to highlight the bottom ones, though. The bottom ones, because we barely, if ever, use these. But pay attention, not just every motor. If I get you a motor and synchronous motor, make sure you go to the synchronous area. If it's energy efficient, please pay attention to the energy efficient. All other motors, DC motor, one motor, go to these areas. Okay, so that's my overcome device calculation. Then you guys are familiar with this. These are the standard fuses that we use in the US, right? And start with 15 amps in the power industry and go press all the way to 600 amps. Now you guys are, you're about to graduate. All these times I used to kill, go to the next standard, go to the next standard. Later on, next week or the week after, we're gonna start talking about, these are for non-adjustable circuit breakers. If you have an adjustable circuit breaker, it opens the can of worms for all of them. So for example, suppose that I have an adjustable circuit breaker, and let's just say my load is, let's say I did the calculation and my load is 3215 amps. I need to find an overcompression device for 3,215 amps. Okay, 3,215 amps out of here. So immediately, Chris, where are you going to go based on that, right? 400.
Over 800 amps.
Yeah, but then you size your conductor to the 4,000. You can, as low over 100 amp. The problem with over 800 amp is if you size the conductor to match the overcompression device, 800 amp become obsolete. You know, so now from here you're going to go to the next standard, right? That's what I told you. Well, guess what? You could have then your big overcompression device is going to be 4,000 amp, okay? And then this most likely is going to be just the box that you bought. Then you're going to have a trip later on. Please pay attention. This is called the trip unit. You're going to have a trip unit right inside the overcompression device, so you can adjust it. That trip unit goes from 0.1 all the way to 1.0. From 0.1 to 1.0 for the most part. What does that mean? So if you did a trip at 0.1 multiplied by 4,000, that will get you 400 amps. Chris, you have easily, by tweaking the circuit breaker to 0.1, guys, you have changed a 4,000 amp into a 400 amp circuit breaker. Let's do 0.5. If you have a 0.5 times 4,000, you get you what? 2,000 amps. I have changed this circuit breaker to 2,000 amps. Please, that's exactly how we do it. When you guys go higher than 1,000 amp, that's how it's done. These become almost obsolete, the sizes. And let's just say, pick another value. And let's go 1 times 4,000, obviously, is 4,000, 0, 0, 0, 10. And in between, anywhere in between. For most of the time, Chris is 0.1 increments. 0.1, 0.2, 0.3, 0.4, 0.5. So basically, how many, all the way to 1. So I have 10 circuit breakers in 1 here, right? 10 of them. There's still, who cares? The question is still, who cares? Here's what who cares. If I set this one at 0.1, my circuit breaker is 400 amp. Chris, we just said that. Your feeder is also 400 amp. So it blows people's minds. I have a 4,000 amp box, and I trip it, set it at 0.1, and I pull a 400 amp worth of a feeder to it. Please understand this. That's how we do it. We don't pull a feeder for 4,000 amp unless we need a 4,000 amp load. So all these sizes that you're looking at, guys, becomes, they call it frame size. Frame size. So if you go Cutler Hammer, Square D, they call all these sizes that you're looking at, it's called frame size. What is the frame size? Frame size is a box. This is a frame size. How big of a box you can fit in this panel? That's it. How big of a physical size circuit breaker you can fit in this panel. Then the trip size is what you're looking at. Everything here that you do is called trip size. And we're going to be doing a few of these. So please just keep it in the back of your mind. We're going to be sizing based on the trip size, not the frame size. So all what Chad have been lying to you all these years about go all the way and extend it, go all the way and extend it. That's true when we're dealing with 1,000 amp or less, even 600 amp or less. You go higher than that, you're going to start jumping into something called trip size. Trip size. Okay, especially when you size your conductors. And we'll
The 4,000 amp one, you can't handle the heat. And I assume there's some advantage to that if you have problems with the
yeah.
Or does it take into consideration both the two things wrong?
When you change this, you go by the worst scenario. The worst scenario, if you're sitting at 1 and you're pulling 4,000 amps, then this box frame must be able to handle the heat and the magnetic force that's coming out of interrupting a 4,000 amp load. That's the worst scenario. Now you go lower than that.
Well, it's a thermomagnetic breaker, correct?
No,
it's not.
Electronics. Thank you. All these, you guys go, yeah, you go higher than, gosh, 2,400. I think the limit is 2,500 for thermomagnetic, and it's still adjustable too. 2,500. After that, it becomes all electronic circuit breakers, all adjustable. Okay, so that's basically what I wanted to show, guys. We got these. The other ones. This is if you haven't seen the system, and I'm going to give you a break quick here. This is, guys, a two-phase system. How the two-phase system looks like in terms of signal, a 90-degree angle between the two phases. Because a lot of you look at two phases, and here's my two-phase system. Just to give you an idea how it looks like versus the three-phase system. I don't know if you can see from here to here. This is where you get the 90-degree electrical degree angle between them. So yeah, that's my two-phase system. And then the rest of it, guys, please review these. Really nice. This is we did them in details. We sized the overload, and we sized the instantaneous trip circuit breaker or whatever, and we sized the conductor. So I'm not going to repeat this. They put them really in a nice format too. Please look at them. That's exactly what we did with Chad. I'm not going to repeat it because we did it in the calc. But the nice thing here, they did it for a DC motor. Can you guys see that was done for a DC motor, which exactly the same. Here's the full load amp of the DC motor. Full load amp of a DC motor. So these are the rest of them is, guys, calculation that we've done. Now it's done here for an AC, an 8 volt with service factor. AC motor with a full load current 3-phase. And then we have an EMF 3, also voltage 440 AC. So all these calculations, guys, done. Please review them on your own time and convenience. three-phase, a couple of calculations for different. This is synchronous with a power factor, Chris. Synchronous calculation, they're giving you a power factor. Remember that what we said, if the power factor is less than 1, what do? We multiply by 1.1, the full load current. They're giving you a code letter doing calculation. Here's what they did. The start point, can you guys see where the start point here is 1.1? That's a synchronous. You up the full load current from the NEC code book. And then they grouped all of them and they put them in a feeder. And the poor man's job, and they grabbed guys and they fed all these equipments from a J box or a pull box and back into the panel. And everything here that you're looking at, guys, it's exactly what we did with Chad in a different format. Same calculation, step by step. So this is hopefully another indication for you guys with a chapter book to emphasize what we have done in the calculation. All the rules are there. And that's basically it in terms of this chapter. Any question, guys? Any question? Again, I can't emphasize, we did all this calculation. The only difference is synchronous motor, you're going to up the current based on the power factor. DC, you're going to go to a different table and so forth. But for the induction motors, which is you're going to encounter probably 70 to 80% of your life, we did the calculation completely. Any comments, any questions? For trip size and frame size of electronic adjustable circuit breakers, guys, later on the coming weeks, we're going to be sizing based later on a lot of when we size things, we're going to go to a trip unit size instead of the frame size. And when we use the software, if you understand what I drew today, when we use the software, it makes a lot of sense. So that's all I have. I hope you guys will be able to print today. I want to go get you the paper, so we'll go from there.